All right, let's get started. Welcome everybody to the Ecosystem of Learning series. My name's Josh Huntsberger, and I'm Executive Director of the Regenerative Medicine Manufacturing Society, or RMMS. RMMS is launching a new pilot series that's free to the public. To learn more about advances happening in the field of regenerative medicine, since it's free, we're conducting a pilot series that has limited enrollment. And after this pilot series, we'll pull the audience and determine how best to hopefully grow this series if there's continued enthusiasm. And we'll also be recording this session. So before we start our program, I did want to make a quick introduction for RMMS. It's a professional society dedicated solely to advancing the field of regenerative medicine. Society members include industry, government, academia, nonprofit organizations, and we're an active group seeking to share our knowledge and work together to create solutions to manufacturing challenges. The ultimate goal is to develop standardized manufacturing processes to facilitate smooth and quick transition of new therapies to market for the benefit of patients. So our first speaker will be Jana Stoudemire. Jana is currently the Director of In-Space Manufacturing at Axiom Space. And Jana is helping to create a new market sectors in the commercial space economy in low Earth orbit and in-space manufacturing of biomedical and advanced material applications on the world's first commercial space station. She transitioned from pharma to lead life science research in microgravity as part of the team managing the International Space Station U.S. National Laboratories, or ISS-NL, then joined Space Tango, where she successfully established the initial foundational partnerships that are helping to define an emerging biomedical market on orbit. And today we'll hear about some of the exciting advances being made to pave the way for in-space manufacturing. And I will get Jana's slides up right now.
Awesome. Thank you, Josh. And I'm really pleased to have the opportunity to talk with everyone today. I appreciate the kind introduction. And since we're focusing on manufacturing, I thought I would talk a little bit about the future of manufacturing and what it's going to look like. And I know that the second part of this session, we're going to be talking a little bit more about AI, and I think it's going to be a super interesting discussion for us. So thanks, Josh. We can go to the next slide.
Certainly. Why isn't it going to the next slide? There we go.
Perfect. Awesome. So when we think about space and the International Space Station, I kind of want to start by grounding us with where we are today. And the ISS is a feat of engineering that has been on orbit, gosh, over 20 plus years. It's coming up on the end of its useful life at the end of this decade. We are all very hopeful that it's going to make it maybe beyond that, but it certainly has, served us well. People have lived on the ISS for the last 22, 23 years now, and it's been someplace that has been a phenomenal laboratory to help us to try to understand more about the phenomena of what we see in changes to biological systems as well as physical properties in space. We're using that sort of decade of results approach now to take what we've learned over the last several decades on the ISS and think about how do we do things in space that we can't do here on the ground, which means make products that are products that we probably can't really envision today because we can't make them here yet, but that will really change the way that we do things. And, I like to think about when we think of a couple of years ago or 10 years ago, when we had cell phones that were just phones, and now we have phones that do everything, and we couldn't have imagined that we could have had a phone that was that capable, but we also can't live without it. The same thing is true for some of the products that we're talking about. There'll be products that we can't envision yet that will change healthcare and change technology. And it will be because we can make them in an environment that allows us to do things we can't do here on the ground. So next slide. So what's beyond the ISS, as Josh mentioned, are commercial space stations. Axiom is building the first commercial space station, and in 2020 was awarded exclusive rights to dock to the ISS. So we're very excited because this gives us the opportunity to put new types of platforms and capabilities in space that not only allow us to continue research with state-of-the-art tools, but actually to think about manufacturing as well. Next slide. Just so that you have a sense of what we're thinking. You know, for us, really, it's about expanding the definition of global. We really want to improve life on Earth, foster the possibilities beyond it, and build a thriving home in space that really benefits every human everywhere. And when we think about that kind of a vision, it really does mean that the idea of in the future, you might actually take a rocket to your job instead of a plane is not out of the realm of possibility. Next slide. So the way that we're working towards having our first module attached to the ISS, first, we're starting with work on the International Space Station to help us to develop proof of concepts. Certainly in this phase, we're also conducting private astronaut missions. And you've probably heard about some of the Axiom missions. I'm going to touch on them in the next slide. But, you know, they're a way for us to help to get ready for having all the systems that we're going to need to have in place. Our own mission control centers, our own ways to load vehicles, splashdown, crew recovery, payload recovery, all those systems, those are getting us ready for when we have modules attached to the ISS, and then eventually when we detach and become a free-flying commercial space station. Next slide. So the private astronaut missions that I mentioned, we've conducted 3, and our 4th mission is scheduled for the end of this year. These missions not only help us to get ready for spaceflight when we have our own modules, but we also conduct a lot of science on these missions. So we're very fortunate to have crews that work very, very hard. These are short duration missions, usually about 10 to 12 days, although sometimes we get stuck up there because of weather and they get a few extra days on orbit, which is great. But we're using these to help us with some of the science as well. Next slide. As I mentioned, you know, the assembly sequence really right now. So the first couple modules we're thinking about obviously need to have crew quarters, they need to have exercise equipment, and they have to have some research capabilities. But the research and manufacturing facility that will be dedicated is something that we're super excited to bring up, and probably we'll bring it up in conjunction with our power tower because we recognize that there's going to be significant power needs. And I think, Josh, even when we talked about biospherics coming into your area and just how you had to reconfigure the building. Yep. So when you think about some of the things that we're thinking about doing on orbit, they're not very different from what we're thinking about on the ground, but it's the first time that we have the opportunity in a space station kind of capacity to be able to think about that. Next slide. So just to give you a sense of where we are, on the right is actually the HAB1 module. Thales Alenia is our partner in Italy. They built all of the modules that are currently on orbit for the ISS. So they are uniquely positioned in the space industry because they have all of the tools to allow the machining that needs to be done for these modules. We're pretty close to finished with that and should be receiving that in Houston, probably the second half of this year. So it's just the outer shell, and then we'll configure the inner configurations of the module. But we expect to have that by, as I say, later this year and to launch and attach to the ISS in 2026. Already in Houston is what we call the multi-purpose logistics module. And I'm sorry that you just have a picture here of this coming out of the plane that brought it to Houston, but this module is very similar to modules that are already on orbit. And in fact, it flew once in a space shuttle as a cargo transport. So it's a facility that we have that we can start to think about, even as we adapt for manufacturing facilities, what this might look like. Next slide. So just a little bit about the inside of the modules. You know, I always love to sort of talk about what a lab looks like on the ground and then what the lab on the ISS looks like. And on the left is kind of the traditional lab, and on the right, that's the International Space Station. And I love the fact that it's got lots of capabilities, but I affectionately refer to this as like the 20-year-old garage, right? Because it's got a lot of things that have come up over the years, has a lot of things that have floated away over the years too, that are yet to be found on the ISS. But the idea for, the way we're looking at building future modules is to really kind of streamline and use those spaces very effectively, but it's more of a everything's behind the wall and a sleeker kind of design that gives us the ability to try to maximize space. Next slide. So a dedicated research and manufacturing facility. The reason that this is important, as I mentioned, the ISS right now gives us opportunities to do proof of concept. But when we start talking about the fact that we really want to produce products, and especially biological products that are intended for human use, we have to be able to separate these areas from where crew are. And obviously, cleanliness is a big factor. Next slide. So when we think about things like manufacturing on the ground, the first thing that everybody thinks about is a GMP facility. So good manufacturing practices are required from an FDA perspective for approval. And I know Steve talked a lot about standards in the last meeting, and
Yep.
sort of those standards that apply on the ground, they're all going to apply in space. There's going to be slightly different standards that we might need to talk about. For example, you don't use settle plates in a manufacturing facility on orbit because nothing settles, right? So we might have a little bit of a different way that we look at how we do particulate counts or, monitor and measure sterility. But for the most part, just like we're going to use the same regulations and follow the same regulations for the types of products and guidance, the standards will be the same as well. But having these capabilities opens the entire biomedical market. And we couldn't do that on the current ISS. And we couldn't do it unless we had a dedicated facility. Next slide. So why space, right? I'm sure a lot of people sitting on this call are thinking, gosh, I don't even get it. But, when you think about taking gravity as a constant force that is something that's around us every day out of the equation, quite literally, right? Biology changes, and so do the way that physical forces and materials act. This is something that I think is really difficult for people to understand. And one of the things that I think is fascinating about some of the projects that we do work on, it helps people to kind of change their perspective when they see science in a different way. And that's, I think, where true breakthroughs happen and where we can really start to imagine the possibilities of types of therapies and products that we can make that we couldn't even imagine today. Next slide. So just quickly walk through the kinds of products and applications that we're thinking about that are in development. And as I mentioned, we use our private astronaut missions as well as the commercial resupply missions that are available to us to access the International Space Station. But it's helpful to be able to start looking at proof of concepts and setting early manufacturing parameters. So we have done a variety of different payloads. And the first one that I want to talk about is the tissue engineered constructs from the Wake Forest team. It's been fantastic to think about building blocks that are a potential bridge to transplantation of thick tissue, looking at things like vascularization. So when you think about how cell shape, cell signaling, and even cell matrix interaction is different, we may be able to identify things that help us to sort of address the challenges that we have with vascularizing thick tissues, eventually building blocks that lead to maybe one day a whole functional organ. We have opportunities to look at things like stem cell manufacturing in orbit as well. And some of the work that has been done has looked at differentiated cells and maintaining a state of pluripotency. Some of the work that we just did on AX2 let's look at the very early steps. If we were to take up a fibroblast and turn it into an iPS cell and then differentiate it, are there things that we see in those steps that actually help us to maybe improve the processes here on Earth? So we're super excited because both of those two projects that are related to stem cells and tissue engineering are continuing on with additional flights, and certainly happy to keep everyone updated on data. But so far, it's looking pretty positive. tumor organoids, drug challenge, the opportunity to use this environment to look at things like cancer. Can we find out more about the disease itself? Can we learn how to predict and prevent? And can we accelerate drug development? So we've done quite a bit of work on AX1, AX2, and AX3, looking at a variety of different types of tumor organoids and identifying compounds that are already FDA approved or in development to try to see if we can see how in an accelerated environment where you see the cancer pathways turn on and be a little bit more active than they are here on the ground, if you use inhibitors for those pathways, can you actually shut them down? And this is super exciting because, from a space perspective, the cancer moonshot is definitely a focus area. And the ISS National Lab just put out a call for igniting innovation that focuses on cancer research and finding models and ways to look at accelerating drug development. That again, with the Wake Forest team, we just submitted an AI-driven application, which you'll hear a little bit more about AI in the next round. And then DNA nanomaterials. So DNA-inspired nanomaterials are really fun to think about because everybody uses lipid nanoparticles right now for delivery systems, which work, but have some toxicity. And as most everyone knows, like when we had COVID vaccines that were mRNA vaccines, they were difficult because of the logistics chain at -80. These kinds of materials that we can make on orbit actually offer us an opportunity not only for reduced toxicity, but these are stable at room temperature. So both for cartilage repair as a first-in-kind injectable matrix for cartilage repair and for mRNA type drug delivery or other cancer therapeutics or gene therapy. Next slide. And then on AX3, in addition to the work that I mentioned before on the tumor organoid models, we also flew brain organoids, looking at Parkinson's and MS. So, when you think about disease modeling and you think about the opportunities that we have to look at biology a little bit differently, these are great opportunities for us to study common pathways like neuroinflammation in neurodegenerative disease. In microgravity, I think that as we identify ways to put models together that help us to not only understand the disease, but help us to test new therapies, we potentially have an opportunity to kind of change the way that we look at research on the ground and maybe make some significant breakthroughs for patients. Next slide. The last thing that I just wanted to quickly mention is the concept of the in-space biomanufacturing hub. So before, after the team won the vascular tissue challenge, and we were very excited to work with the RegenMed Hub because clearly the team is expert in tissue engineering. So Axiom had established a partnership and we started to go down this path of what would it look like to do some research in space. And I'm very pleased to say that, the NSF Regional Engine Award, the inaugural awards that the Wake Forest team just actually secured, it actually contains an in-space manufacturing ITech, so an innovation technology education core. And as we think about how we're going to build out for the future of biomanufacturing, we're very much thinking about how we bring in space manufacturing and some of the tools that will help us to do that, like AI, which you'll hear a little bit more about next. Next slide. Just so that you understand that Axiom is not alone as we talk about what's going to happen in the future. We often say we have the privilege of going first, but we also carry the responsibility of doing it well, because there are several other commercial space stations that are also in development and looking at the opportunities similarly to how can we manufacture things on orbit. Right now, we don't have, it's early days, and so we don't really have enough manufacturing to maybe need 3 or 4 different commercial space stations, but we certainly envision in the future that that potential will be there. And, the estimates for these markets are in the trillions of dollars because everybody recognizes that the potential, the satellite industry really just takes advantage of the vantage point, observation, and communications, but it doesn't harness microgravity. And as we think about how we're really going to be able to realize that potential, we're going to need every bit of this room. So by the end of the decade, Axiom will be a free flyer, and hopefully we'll have several other stations up there with us. Next slide. That's it. I think that's it for me. Happy to take questions now or after we go through the next presentation.
Yeah, if we could maybe try to hold questions till the end, that way we can transition to the next speaker. And actually, what I'd suggest, so you don't lose your question, is put it in the chat, and then that way we'll start right there. But excellent talk, Jana, as always, brilliant. And so exciting to be thinking about what does this future look like of in-space biomanufacturing. So our next speaker is Dr. Hans Müller Paul. Hans currently works at Oracle Health in the digital health and AI ML innovation space. He advises internal and external stakeholders on AI and ML model development and implementation strategies, modernization of existing products, and digital transformation. He also presents at conferences, and he's actually at one right now, and produces content for thought leaders on the use of AI and ML and emerging technologies at the forefront of healthcare. Today, we will hear some of his perspectives on automation for manufacturing and how this is critical for optimization using AI and ML models. I think I enabled screen sharing. So Hans, take it away.
Thank you, Josh. Thanks everyone for joining. Hope you guys can see my screen.
Looks good.
All right, sounds good. So I just came back from a conference last night, and it's interesting that this talk sort of aligns with conversations that I was having at the conference. And so this was an interesting alignment. It was not planned, but I'm here to talk to you about AI, automation. And I know that everyone kind of wants to use AI for their research right now, but there's a lot of misconnections between what are the capabilities. Sometimes we have a little difficulty understanding what are the limitations, what can be done, what cannot be done. And one of the big challenges with using AI on research is that we've probably all heard someone saying that AI is only as good as the data that it uses. And so if you don't have a good data set to train your AI, that really limits your ability to have good results, right? You need a good structure, a robust data infrastructure, so you can have good predictions. And AI is only able to predict based on things that it has seen during training. So we can't expect to train a model with a very small data set or a very poorly matched data set from disparate sources and have robust predictions, right? And so we need to be able to recognize that this is one of the challenges, and that when there's problems with the data, that has an impact directly on our conclusions. And so to understand a little bit more of how this works, this is the classical predictive AI training process, where we take large chunks of data and we run them through an AI model to get like a trained model at the end. We learn the connections between those data points and other factors. But the goal is, when we have this trained model and we want to make a prediction with some new data, we can just port this trained model, present it to the new data, and this enables us to get a prediction of what we expect to see experimentally. And if we have a good model, and when we conduct the experiments at the end, we're going to see that it matches what our predictions were from the model. And this is the ideal use case, and this is where we want to get. Because once we have a good, robust model, this means that we can trust the results that are being generated from these predictions are good enough that we can just incorporate them into our asking of more complex questions, right? We can use those as a baseline, and this enables us to accelerate research grandly. But there's two very big issues for when you're dealing in this space, especially in the life sciences and biomedical research space, that we run into constantly. And those are, you probably are familiar with them if you've tried to do any of this type of research in the past. The first one that I'm going to cover is data silos. And so the data is siloed. And so we have many institutions doing similar types of research. They all have their own data sets. They all can develop their own AI ML models. They can make their own predictions, and they can generate their own insights. But they're each guarding their data set, because if they share this data, other people will know what they're working on. There's this very strong culture, especially in academia, of withholding your secrets, and you only publish once you're ready to have your next paper published, so that no one has enough time to outcompete you and scoop your research, right? And what this leads to is us having to deal with this silo situation where together we would have very robust data to train models potentially, but since we are all limited by the data that we have at our institutions, we end up being limited on the scope of the models we can develop with them. And one of the ways that we can approach this type of problem, and this is not the main focus of this conversation, but I just wanted to leave it out there, is working with a federated learning model, for example, where we have an additional layer here at the beginning, which is a federation layer. And this basically enables each of these sites to contribute their data in a way that is anonymized, and you can use this in a remote environment where you cannot reverse engineering anyone else's data, but the data is anonymized and combined. And what this enables is a more robust machine learning model, because data is king, right? Data is everything. And so if we have access to data from different sources, that enhances our ability to make good predictions. There's, however, one drawback to all of this, which is the data standardization conundrum, right? So I love this comic because it says, it depicts the image clearly. And this is a problem in the tech world, but it's also a problem in the lab world, where we have too many competing standards. And then someone tries to come up with a new standard that is going to solve all the problems. And now we have one more competing standard, right? And this is very true. If you've ever worked in two different labs that work on the same field, you will know that they have different protocols for everything. And they have, the implication of this is that sometimes the results are not necessarily comparable, right, between different institutions, or even between different people in the same institution, because even though there's like a standard procedure that everyone's supposed to follow, some people are able to come with tweaks that make it either more efficient or have better results or work in less time. And so even within the same institution, we have variations in the results that each individual can generate. And even if, for example, if Josh and Jana and I worked in the same lab and we all did the same experiments, we could be very consistent. So my results would always be consistent and Josh's would always be consistent. There would be differences between me and Josh and how we get to the results. And that type of variability inside an institution can already cause the problems when you're using other people's data to run your models. Imagine doing this across institutions where besides those limitations, we also have different protocols being followed and different steps. And how do you compare data if the conditions are not all the same? And this is one of the big issues that we need to address. And like I said, one of the biggest factors for AI is the amount of data you have. And we now run into the limiting factors of generating this data, right? So here I have like a very real graph that is totally based on data. That is the number of experiments that can be performed versus time. And these are not arbitrary, okay, but if we have one person working on the experiment, let's say we have this, however much time this one person spends working on this, they can do this number of experiments. And so if you need more results faster, you can hire more people. And as you add your second worker, you can produce results faster. And as you add your third worker, you can produce results faster. But there's a limit to how much each person individually can do. There's a limit to how many hours they're able to work. There's a limit to the ability of the human brain to do multiple tasks at the same time. And so what we run into ultimately is that if you look at the total production cost by the number of experiments, it grows linearly in this experiment, right? Because if we want to have more data, we have to have more people and they have to work more hours. And so it costs more money, both for their hours and for hiring more people. And so this is where generating more data becomes expensive the more data you're generating. On one concept that tries to address some of these issues is the concept of biological foundries. And so I don't know if you're familiar with this term, but this was the focus of the talk I was giving at the other conference that I was at. And so biological foundries are fully automated lab facilities. And what this enables you to do is, well, first of all, address the standardization problem. If the same machine is doing all the experiments, you remove the variability between individuals. And those are very versatile, and you can build them however you want. This picture is from the Illinois Biological Foundry for Advanced Biomanufacturing. This is in my former lab at the University of Illinois. And so I'm very familiar with this one in particular, but I'll show examples of others. And this is very modular. And so you can see you have your regular day-to-day lab equipment, right? So you have your PCR machines, and you have your centrifuges, and you have your stacks of Petri dishes and biological hood and incubators. And so whatever type of research you do, you can assemble one of these foundries to match the type of resources you're going to need, the type of equipment you're going to need. And the other main advantage is that since each of these pieces is a separate machine and it's fully automated, we don't run into the problem of the limit of how many hours someone can be doing this. And we also don't run into the problem of how many things can be done simultaneously, because each machine can be operated individually. And so you can do one PCR right after the next, and you can plate one sample right after the next, because once this one step is done, it's handed to the next piece of equipment. And so this enables a much higher throughput than would be able to achieve with people doing this type of tasks. Obviously, this doesn't apply to any type of research, and this is not about to take anyone's jobs. But what this enables you to do is to have very consistent results and generate them in very large quantities in a way that would be prohibitive to do with humans doing some of those tasks. And those are very basic and repetitive tasks, right? So those are very easy to automate. So I'm going to show a couple more pictures. And so this is from the NIST, so the National Institute for Standards and Technology. They have a biological foundry as well. And so here we have a few pictures of the inner workings. This is a liquid handling machine inside the foundry. And what it enables you to do is to automate pipetting of anything that you need to pipette into your 96 well plates, or you can even do larger plates, and you can do multiple plates at once. And so this is all in a contained environment. And then once your plates are done, there's this mechanized arm that can pick it up and move it to a different location. And if you need to move it to a different piece of equipment that is far away, you also have these larger arms, and sometimes they are on rails. And so they can move around, and they can carry your experiment to the next station. And so in this case, you have PCR machines, and here's where the plating happens, the pipetting happens, and the liquid handling happens. And so you can have all of those processes happening. Part of the use case that I did on the biofoundry here in Illinois was with genomics. And so I thought it was interesting to show you the Edinburgh Genome Foundry. And so this is one of the larger ones that I have seen in terms of just space and area. And so here you have your rails where your mechanized arms move, and they can move your samples around. And for genomics and other omic type assays, for example, I was using it for CRISPR, and this enables you to do tens of thousands of CRISPR mutations per day because they are fully automated, and you can just run them continuously, put them in the PCR, and as soon as that's done, you can put the next one. And so you can do much more than I could do manually when I was in the lab, that's for sure. And so this enables you to generate very large amounts of data that is high quality data, that is very consistent across runs. And so when we're talking about moving into space, for example, where you have the cost of the travel to the space station, and you have the cost of having people there, and you have all of these different variations in your environment. Of course, if we're going to build a biological foundry in space, it's going to need some new design. This style of design where it's a large room probably wouldn't work in a space station, but the concepts could be applied where it enables you to have a replicate foundry on Earth on regular gravity and one in low orbit. They are the exact same layout, they have the exact same equipment, and it enables you to do the same experiment in both scenarios. And so Jana was saying that gravity heavily impacts the way that the cell biology works, right? And so, but we don't fully understand all of the impacts of gravity. But if we're able to replicate the exact same experiment to a very high consistency on both scenarios, right? On normal gravity and on low gravity, we can use machine learning to then learn what are the differences in the results and how they correlate with the variables that we know are different, which in this case is gravity. And with time and with the ability to generate a lot more of these results very fast and very consistently, what this can enable us to do is generate predictive models after we've created large enough data sets that are high quality. And so this enables us to then, in the future, when designing new experiments, be able to predict the effects of gravity so that it's no longer an unknown variable, right? And then we can actually advance science in low gravity by just inputting a predictive variable. And so we were talking about, as kind of the final point, the cost of generating new data when humans are doing the work and you have limitations of time and ability to do multiple tasks at once. And how does that compare with creating a biofoundry? And obviously the biofoundry has a cost of building it and creating all of these automations, right? And so if you're looking at the scalability of the automated laboratory, your cost is very high at the beginning. And so if you're just going to run few samples, it's obviously not financially viable. But the more experiments you perform on that biofoundry, the cost goes down and down, because once it's assembled, you have the cost of maintenance of the equipment, but equipment maintenance is something you have to do on your regular lab as well. And so what this enables you to do is generate a lot more results, and the more results you generate, the lower it costs for each of these results to be generated, right? And so there's like an inversion of the situation where it gets cheaper the more you do. So it's not worth it if you just have a few experiments that you need to do, but this enables you to scale this type of research to the degree where it can enable better and more robust AI ML in the future. And I think this is all I have for you today, and we can open for questions now.
All right, great. So if we can use the chat function for questions, and I know that Steve put in one that we can jump to right off the bat once I get my chat window up. So this one's to you, Jana. Jana, excellent talk. Thanks. Can you talk a little bit on the possibility of space to Earth delivery of products?
Yep. Well, and thank you for that question, Steve. And also, Hans, you know, it's interesting because when we talk about, I really loved in your talk when you were sort of envisioning this concept of not only predictability, but sort of automation in space. And I think when we think about our future factories are always something that everyone's interested in, right? And automation is going to be a key component, especially on a space station from a manufacturing perspective, not only for the efficiency, but to take people out of the process for batch records and things like that. But one of the things that is always really interesting is as we think about design too, we're thinking about there's no up or down, so we can use all four surfaces. So like an isolator doesn't have to be straight. It can be 360. And when we, and so some of those concepts, I think are going to help in the terrestrial side of the field as well. It's just like the question Steve is asking from a distribution standpoint. So logistics for us back and forth on a rocket, yep, it's, you know, interesting because rockets don't always launch on time. And so if you're trying to launch something at 37 degrees or any kind of temperature condition, you either need power in your vehicle to do it, and you also, when you bring those products back, need to have sort of a controlled re-entry. So whatever temperature they need to come back at, how they go into the distribution chain, those are pieces in the process that are getting much better. Our access to space is, in fact, so robust now that we have issues of traffic at station. So sometimes you have to wait for someone to undock to be able to have a place to dock on the International Space Station because vehicles are going back and forth so often. But in the future, you're also going to have orbital transport vehicles, kind of like a FedEx to space, right? They're not necessarily the commercial resupply missions that just happen every 6 months. They are missions in between that help us to move product from one location to the next. We have vehicles like Dream Chaser coming online. And, you know, I jokingly said at a conference that I was at with Ken Shields from Sierra Space, because they talk about how the Dream Chaser is very much like the shuttle. It just needs a runway to land. It doesn't splash down in the ocean. So all they need is a big runway. And I'm here in San Diego, and we actually have this big airbase called Miramar, and they have this massive runway. And so we were in a panel together, and I actually said, when someone said, what's the future going to look like? And I said, well, Ken's going to land my payload right in my backyard, and I just go pick it up, right? So from a distribution standpoint, you know, there's considerations for temperature control, for chain of custody control, but there's also increasing cadence of vehicles and opportunities for how we're going to be able to not only access microgravity, but bring them back, bring products back. I hope that answers what you were asking, Steve.
Yeah, can I say something?
Sure.
Yeah, that does. I was also just interested in this prospect of being able to deliver anywhere on Earth at a faster cadence.
That's true. Well,
yeah.
And the other thing that's really happening, and you know, this is kind of a by default, the space industry, everybody hears about the commercial space and you hear about Space Force, but I don't know that, you know, it's very visible to everybody that some of the work that's happening even at that level for Space Force to be able to transport troops anywhere in the globe, like within 4 hours, they're really developing hypersonic flight capabilities that are aligned with launch vehicles, but that would stay just sort of above the Kármán line. They don't go, you know, 250 miles up. They're only like 60 kilometers up, right? But at the end of the day, you're sort of thinking, how does that distribution chain then come into play when we're thinking about things like organs and organ transport?
Yeah.
So if we have an organ that today we couldn't get to somebody because it happens to be international, but someone needs it here in the US, in the future, that's not so far-fetched to think that some of those transportation byproducts that are coming out of the space industry for lots of different reasons could really have an impact on our industry as well.
Yeah. And we have BMI Organ Bank actually on this call, Carrie. So the future is BMI Organ Bank, you know, partnering with Axiom Space and within 4 hours delivering organs anywhere around the world.
There you go. There you go, Jana.
I know. Well, and
it.
What's fun to think about too is like right now, because we don't have those kinds of capabilities, we have to think about alternates, like how do we transport at temperature and maintaining CO2 at some levels and extended over extended periods of time, right? There's nobody that even has a container yet that can keep CO2 or hold CO2 for more than a couple of days. So if we're talking about live cells, it starts to get hard when we're talking about 48-hour periods. But in 4 hours, the types of transport systems that we're even going to need, if we have accelerated timeframes like that for delivery, it's just, it changes the whole industry. Like, once again, it changes like the internet, the way that you do everything, right? When before we had it, we couldn't imagine what we would use it for, and now we can't live without it, and we do everything. So those are the kinds of changes that I think the space industry represents that are going to become really entrenched in some of the things that we do here on Earth, just because they're going to be much more common, and you're going to see commercial companies doing this, and it's an infusion of ideas and innovation.
Yeah. The next question that I'd like to ask, and I want to piggyback off of Sita's question on workforce development, but I'd like you both, since we see AI and machine learning and in-space biomanufacturing as disruptors, we're going to need a whole new workforce. What do you both envision, for special workforce development needs for in-space biomanufacturing and AI and machine learning? And how do we train that workforce for these new jobs?
Hans, do you want to go first?
Sure. And Russ just sent a similar question now, and so I'll go address that question. So there's the question was, what AI technical skills will be needed by lab workers? And those are, in my opinion, two separate sets of skills that we would need. So we will still need people with the lab technical skills that we have now, and the people with the AI technical skills will be a separate subset, right? So they need to be able to work together. And one of the big challenges here, and this is something that I've seen a lot, is the difficulty in communication between those two groups, because they definitely don't speak the same language. And so that's probably the first barrier that you need to think about. But you would need two separate teams, one to understand the technical aspect of the lab, the biologicals, the reactions, the growths, the cultures, and one that understands the other side, the programming of the automations, the data analysis, the underlying assumptions that you have to do for your statistics to make sense at the end. So those were two separate groups that you have to have combined if you're targeting having this type of modernized AI-based workforce in the future.
Yeah, and I mean, I'll add on from a space perspective, because I saw the question from you too, Russ, like, would it be a mission specialist or so? So we talk right now about the fact that, it's great that we have in our private astronaut corps, we actually have people that have skills, right? Just like our Peggy Whitson she's a biologist at heart. And so it's when we have someone like that on station, that's fantastic. But we also envision having the scientists who actually are responsible for doing a lot of this work, flying with their own payloads, not too far in the future. NASA has proposed several times that they would like support to what they call them instead of mission specialists, they call them science specialists, right? So that it's sort of because the idea is that really it's anybody who has the technical skill to work in a manufacturing facility or in a lab is the type of person that we're going to be wanting to go to space. And workforce development, when you talk about from a space perspective, there's a lot of peripheral industries around the space industry, in addition to the skills that we need, skilled workers in biology, biotech, manufacturing, and understanding. So jobs that you would think, how would my job ever relate to space? It's going to be there in a few years from now. As we create these GMP facilities, we need to have people that know how to work in those, and that's their new work environment. But along with that, we have a lot of opportunities for the distribution chain. So as we open up the distribution chain, we need people that can do logistics and transport. In space, everything goes to the International Space Station in what we call soft stow or soft goods. So we have a lot of sewing needs, right? There's a space career that most people probably don't even think about. But we need a whole force of people that are helping us to make all the bags and all the pieces that we use to assemble packs for station and everything that's being transported on the way up and down. I think that the take home for me here is that workforce development for the space industry, it includes almost every job you can think of here on the ground, because it's going to be a part of the space industry, and the space industry is going to be a big part of the future. So whether it's putting together nutritious meals for people who are living and working in space, because that's a little different in terms of dietary needs than here on the ground, whether it's space law and policy, whether it's patent attorneys, you name it. I mean, they're going to be a part of the space industry. And I'm very excited because in the NSF engine, a lot of the workforce development programs that we need to stand up, I'm so happy that we have a component for space. The White House has an initiative to build the next generation workforce for the space industry. And we're going to combine that with some of the work that we're doing with the NSF engine to really help to grow a community that understands space is the future of manufacturing. And I think that when we start to think about some of the methods that we can even use, like AI, like virtual reality, it's not going to be so far-fetched to say that you can train somebody and they could be watching a procedure from somewhere far away, whether it's on the ground or in space, that would help them to identify how they could be a part of that in the future. Russ, I see your hand up.
Hey, Jana. Yeah, you know where I am on this. I mean, I'm in heaven right now, so this is great. Thank you so much. Yeah. No, it's really interesting. I just did a project with Biomate, which is Department of Defense sponsored, and it was looking at nanosoils and using DNA sequencers, handheld, mini ion, and also a tabletop scanning electron microscope. But what was really interesting the woman behind it and her husband were both ground specialists for NASA, and they had been on the shuttle. And she had gone back and she was an engineer, he was an engineer, and she had gone back to do her PhD in bioinformatics. And when you started talking, I kept on thinking to myself, and then her husband actually had gone back and been a science teacher in high school. So they reinvented themselves, right? But I kept on thinking, oh my gosh, they have all this experience, and they probably don't even realize that within 5 years, they're going to be in high demand because they've been putting people into space. And at the same time, they've upped their skills. And so very, very interesting people. So I just wanted to sort of throw that in there. And of course, my cells are going to space.
Exactly. Well, no, and that's so helpful, Russ, because seriously, before, and it's been an interesting transition even from a NASA perspective. So initially astronauts, right? When you think about astronauts or you think about someone going into an aerospace career, it's somebody who knows how to launch rockets, propulsion, or maybe robotics. And even the initial core of NASA astronauts, they weren't scientists, they were builders because they had to build that International Space Station before it became a laboratory. Then as you start to look, later in the core, we have people like Peggy Whitson or Kate Rubins, who came out of UCSD. We have people who are hands-on biologists on the ground that transitioned over. But I think what you're going to see is that it's not about rockets and propulsion. Yeah, there's still going to be that industry for engineers, but now think about everything else that is an industry that we have here on the ground, whether that's technology or biotechnology. And those jobs are going to be jobs that are going to be translating to space. So that is one of the most valuable skill sets that we can bring across are people who already have that experience here on Earth. When we translate that up to space, we can kind of teach them the new logistics part about going to space, but they already come with that solid background for what we need from an industry.
Yeah. So I think we're about out of time. I know we have more questions, and I had a list of about 5 other questions too. But in the interest of time, I think we'll conclude. But just want to thank our speakers.
I just want to make a comment. I answered 2 of the questions that were on chat. We don't have to answer.
Oh.
So there are
Hans,
answers. If you ask the question, please go check.
You're faster than me, Hans. I haven't gotten back to that yet.
Hans, do you want to just real quick mention that since you answered the question?
Well, I think we're going to run out of time if I do.
Okay.
Please
all
feel
right.
free to chat. Ask the question.
And I'll take these
as well. Questions.
Yeah, I'll take these notes and summarize them with everybody that attended too. All right. Well, thanks again, our speakers. Wonderful, and this is the future, and it's so exciting. This path that we're on is pretty tremendous. So exciting roads.
Thanks, guys.
Take care. Bye, everybody.
Bye.
Thank you.
Bye. Thank you.